Hello everyone, my name is Yuhang Zhou. I'm from the research group of Professor Feng and Cai at Southeast University, Nanjing, China. The title of my presentation is Analysis of Bargaining Behavior of Tubular Braces based on non-rigid origami patterns. My presentation is mainly divided into the following parts: introduction, selection of origami patterns, bargaining behavior, and conclusion. In the field of civil engineering, equipping bargaining restraint braces is an effective method to improve the energy dissipation capacity of important structures. As the theoretical experiments carried out by the team of Tsinghua University, two ordinary braces were bucked in a steel frame, but the steel frame with the two BRBs was in good condition. As it was confirmed by the experiments, a large amount of BRBs will be adopted in Tencent Global Base in Shenzhen, China. As shown in the motion graph, a BRB maintains a good performance under the compression load. The main components of a BRB are shown in this figure. The spatial configuration of BRBs transforms the bargaining mode of the braces from low order to high order, making more areas to yield and dissipating more energy rather than bargaining. Different from the BRB principle, there are other ways to induce the bargaining modes. A series of dents or holes were introduced to the thin-walled steel tubes to testify the controllable energy absorption performance, and some origami tessellations were formed on the surface of the tubes to change the deformation modes under the impact load. Our research group has carried out research on a variety of origami applications, such as the four-crease twinning deployable membrane, honeycombs, the vibration isolation system, and the deployable roof. And then we thought about how can we effectively design and use origami in energy-dissipating braces. As the widely used rigid origami configuration, the touch pattern was first introduced into the bargaining controlled braces. The braces was composed of the central yield segment and the two-end restraints for easy connection. As a representative of a rigid brace, the movement and energy dissipation mainly depend on the creases on the braces. Both theoretical tests and simulation were conducted. Obviously, the curve of the BCB keeps full, indicating more energy dissipated, but under the same steel consumption, the bargaining controlled braces has a weaker building capacity compared to the ordinary tube. To improve the problem, three different non-rigid origami patterns were selected and designed. They are pyramid, crash box, triangular origami patterns. The three braces based on non-rigid origami include 15 identical units stacked in the z direction. We kept the similar geometrical parameters in the design process. For the above braces, the mechanical responses including stress and deformation distribution are shown in these figures. For the pyramid pattern, crash box pattern, and square tube, the stress values in the middle area are much larger. However, the triangular pattern has a more uniform stress distribution along the axial direction of the brace. From the figure below, the lateral displacement of the triangular pattern under the axial compression is the smallest. The actual force displacement curves of the braces based on origami patterns are shown in this figure. Except for the triangular pattern, the other three have obviously loaded descent stage from the simulation result. The square tubes has the highest load capacity. and elastic stiffness, but soon enters the decline stage. Compared to the others, the brace based on the triangular pattern has the smallest axial elastical stiffness and the lowest yield or peak load, but only a small load drop radar. That means the triangular pattern is more prone to produce the axial deformation rather than the out-of-plane buckling mode. And the longer plastic flow amplitude length makes the triangular pattern more suitable for energy dissipation. For the triangular origami pattern, some important geometrical parameters determine the configuration of the units, such as the number of polygon edges n, the side length a, the torsional angle of the section theta, and the thickness of the place t. The influence of these parameters on the buckling behavior of the braces was analyzed. The model parameters of all 12 designed braces were listed in the table. The models can divide into 4 groups to discuss the influence of the different parameters. The simple conclusion can be seen in the first displacement curves of the 4 groups. The peak load, elastic stiffness, and the drop load are increasing with the increase of the number of polygon edges, the thickness, and the decrease of the side length, and the torsional angle. As a summary of the above research, the following conclusions are obtained. Thanks for listening.